Hello, in this video I'm going to solve the following gold level problem, one variable calculus, improper integrals. This is a problem from India. The following integral from 0 to infinity, ln of 2x over 1 plus x squared dx converges to. Pause the video at this point and give it a try to see which one of the following given options is the correct answer to the problem. Okay, so if you see the options given in this problem are four numbers, so the designer of the question guarantees for us that this integral indeed converges, and we are supposed to find the value to which this integral converges. Okay, so I will also do this. So the solution that I present for the first part of the video is taking into account that yes, this integral is convergent, and I'm just seeking to find the value for which this integral converges to. Okay, and then later in the second part of the video, for the students who are interested to see how they could discover that in principle this integral converges, I will present the usual method of seeing that if this integral converges or not. Okay, so this integral, I am taking it for granted that this is convergent, and I want to find the value to which this integral converges. To do this, I want to show you a theorem. So if we have this integral from 0 to infinity, f of x dx, if this integral converges, it is guaranteed that this integral from 0 into infinity, 1 over x squared, f of 1 over x, dx also converges. Moreover, these two values are the same. So here I am assuming that the left hand side converges. I am claiming that the right hand side converges to the same value to which this integral converges. To prove this, I will introduce a new variable. I will consider u to be 1 over x, and then from here x becomes 1 over u. And then this means that dx is minus 1 over u squared du. On the other hand, the variable x on the left hand side here goes from 0 to infinity. So this implies that the new variable goes from, if x approaches 0 from the right hand side, then u approaches plus infinity. Yes, if I replace x with 0, u becomes plus infinity. And then if I replace x with infinity here, then u becomes 0. So u approaches 0. Okay? So this means that the integral from 0 to infinity f of x dx can be written as integral. Instead of going from 0 to infinity, I go from infinity to 0. And then instead of x here, instead of f of x, I write f of 1 over u, because x is 1 over u. And instead of dx here, I replace it here, something like that. So it becomes minus 1 over u squared du. Then what happens? I use this minus sign to flip these two limits, so it becomes integral from 0 to infinity. I would write 1 over u squared first, and then I will have f of 1 over u du. Okay? So I was able to show that the value of this integral, if it exists, is equal to the value of this integral. Okay? But now you know that the variable of integration for a definite integral is a dummy variable. So it doesn't matter if you change the name of the integration variable to another name, to another letter. So for example, you can change u with alpha everywhere. You can change, I don't know, a u to z everywhere. It will not change the value, yes? Now I would say that, okay, because it is not sensitive to the name of the variable, I can also change u to x itself, yes? It doesn't mean that u and x, I'm not assuming u and x are the same, because you see that they are not the same. But the logic is different. I'm saying that I was able to show that the value of this integral is equal to this integral, and I know that the value of a definite integral is not sensitive to the name of the variable that you choose for integration. So now I am saying that because it is not sensitive to the name of the variable, so it doesn't matter if I change the name u to x. So that's the logic here. So this becomes integral from 0 to infinity 1 over x squared f of 1 over x dx. Okay, so I was able to show that if the left-hand side converges, the right-hand side is also convergent and converges to the same value. But be careful, if the left-hand side converges, which by the structure and the design of the question, it is guaranteed. Okay, so this integral now I want to calculate its value. So if you don't mind, let me call it I. So I is integral from 0 to infinity ln of 2x 1 plus x squared dx. Okay, according to what I just showed for you, I can also be written in the form of 0 to infinity. So you see what's happening. I would write 1 over x squared and multiply it by f of 1 over x. F of 1 over x means that if this is your f of x, go into your f of x and replace every x with 1 over x. Okay, so I will do that. I will put 1 over x squared multiplied by everywhere I see x, I put 1 over x. So it becomes ln of 2 over x. And then I will have 1 plus 1 over x squared. And then I have dx. Okay, and now what I do, I will multiply this x squared here. So this becomes equal to integral from 0 to infinity ln of 2 over x divided by x squared plus 1 dx. Okay, so what I did, I was able to show that if you call this integral I, then I can also be written in this form. Okay, now I will calculate I plus I. For the first I put the first integral from 0 to infinity ln of 2x over 1 plus x squared dx. And for the second I write integral from 0 to infinity ln of 2 over x over x squared plus 1. Because these integrals are assumed to converge, so I can combine them into one integral by writing one integral and adding the integrands. But the good news is that the denominators are exactly the same, so when I want to add them, I write x squared plus 1 as the common denominator, and then I start adding the numerators. So 2x plus ln of 2 over x dx. Okay, but we know we have a formula that's ln of a plus ln of b can be written as ln of a times b. So I will use this formula in the numerator here. So this becomes integral from 0 to infinity, and then it becomes ln of 2x multiplied by 2 over x divided by x squared plus 1 dx. Okay, but the good news is that this x and that x are now cancelled, and 2 times 2 is 4, so it becomes ln of 2, but ln of 2 is a constant, sorry, ln of 4 is a constant, I pull it out, so it becomes ln of 4 integral from 0 to infinity, and then I have dx over x squared plus 1. Yes, but be careful, this is I plus I. Okay, so I plus I is this expression. Okay, but I plus I is just 2I is equal to. And then ln of 4 can be viewed as ln of 2 to power 2, and this 2 goes back. So it becomes 2 ln of 2. But this integral is very simple, yes, because this function is just a derivative of arctangent. So it becomes arctangent of x. X goes from 0 to infinity. Of course, 0 to infinity means 0 to some number r, and take the limit as r goes to infinity. That's what we have to do, but that's more or less the same here now, okay? So now what happens, these 2 here on the left and these 2 here on the right are cancelled because I'm looking for I. So then it becomes ln of 2 multiplied by arctangent of infinity, which is pi over 2, minus arctangent of 0, which is 0, so it becomes pi over 2. So this means that I is equal to pi over 2 ln of 2, which is the answer to this integral, if we already know that this integral converges. So as you see, option D is the correct answer to the problem. Okay, now I want to show, this is actually this is the solution of the problem. The problem is finished here. And based on my experience, I realized that in Indian questions they are using this fact quite common. So that is a very known formula probably there, because they are using this trick in many questions in their JEE advanced exam. So it's good to know about this fact as well. Okay, so as far as this problem is concerned, the solution is complete and finished. But let us change the problem. Okay, if I want to really rigorously do the problem, I have to, because this formula only works if someone guarantees to me that this integral converges in the first place. Okay, so now let us see that is there any way for us to understand that this integral indeed converges, so everything will be intact. Okay, everything will be completely rigorous here. Okay, that is the second part of the problem that I want to start doing now. Okay, the first thing that you have to recognize is that this is an improper integral of both types simultaneously. Yes. First of all, I see the limit here is infinity. This is an indication that this is an improper integral of first kind. And this 0, because when I take the limit of my integrand ln of 2x over 1 plus x squared, as x approaches to 0 from the right hand side, then it becomes minus infinity, because ln of 0 is minus infinity, and then the denominator is 1. So this means that the function is also indeed unbounded when I approach 0, when I am close to 0. Okay, so this is a proper integral of the first type because of the existence of the upper limit to be infinity, and it is also an improper integral of the second kind because when I take the limit as x approaches to this lower limit, it becomes unbounded. Okay, and then based on what you have learned in your calculus course, you know that if you want to treat this integral, you have to consider two integrals, one so that each one of them is improper of only one type. Okay, so in other words, you need to consider two integrals, and one integral from 0 to some positive number c of that function, 2x dx, 2x over 1 plus x squared dx, and the other integral starts from c up to infinity, ln of 2x and 1 plus x squared dx. Okay, of course, c, this is up to you to choose. If you find one particular c for which this integral and that integral simultaneously converge, then this integral by definition converges. And of course, in principle, if you can find the value of this integral for that particular c and the value of this integral for that particular c, if you add them up, then it becomes the result, it becomes the value of the integral. But here the goal is not to find the value of the integral because we already did that part. Okay, we want to really convince ourselves that the method that we used in the previous solution is indeed valid. To do that, I have to show that this integral converges, so I have to make sure that each one of these integrals for some particular choice of c, positive number c, are both convergent. Okay, but because ln, you know that ln of a number box is positive or negative depending if box is greater than 1 or less than 1. Okay, so this might motivate me already because I don't want to have a mixture of signs, positiveness or negativeness for ln of 2x. So let me choose this c to be 1/2. Okay, so that is one guess for c. Okay, so from now on, if you don't mind, let me clean this c, and I want to consider two integrals, one from 0 to 1/2 and the other from 1/2 to infinity, and I want to convince you that both of these integrals actually converge. Okay? Okay, first let me call this integral j1 and start talking about j1. The first thing that I have to do, I have to replace 0 with some epsilon. So I would say epsilon to 1/2, and then I would write ln of 2x and divided by 1 plus x squared dx. And I have to take the limit of this expression when epsilon goes to 0 from the right hand side. This is what I have to do for calculating j1. So in principle, j1 should be this limit if this limit exists. Okay, but now look here, I will consider the absolute value of the integrand here, ln of 2x divided by 1 plus x squared. And I know that this becomes equal to the absolute value of ln of 2x divided by absolute value of 1 plus x squared, but 1 plus x squared is always positive. And this is always smaller than, this is less than absolute value of ln of 2x. But be careful here, because here I am working in an interval for which x is somewhere between epsilon and 1/2. This means that x is less than 1/2, so it means 2x is less than 1, so this means that ln of 2x is indeed negative. So this means that this can be written as minus ln of 2x by removing this absolute value sign. Okay, so I was able to show that this function is less than or equal to this function. Okay, so if I can show you that this integral from epsilon to 1/2 as epsilon approaches to 0 from the right hand side converges, based on the theorem that you have in your calculus course, it is guaranteed that this j1 is also convergent. This integral also converges. Okay, so how should I do that? Okay, so I would say that let us concentrate now on this integral. Integral from epsilon to 1/2 minus ln of 2x dx. Okay? Okay, one way to do this is to calculate this integral, and this is not a hard one. So for example, let me take 2x to be t. Then this means that dx is 1/2 dt. And then if x goes from epsilon to 1/2, this implies that t goes from 2 epsilon to 1. So this means that this integral now becomes equal to minus integral from 2 epsilon to 1 ln of t, and then instead of dx I put 1/2 dt, so I write dt here and I write 1/2 there. But this is a very standard integral, so you can use integration by parts to calculate this integral, yes? So let us do that. I will take this one to be u, and I will take this one to be dv, and I want to use the famous formula for integration by parts. Integral u dv is equal to uv minus integral v du. Okay, and of course here if it goes from a to b, I have to calculate this from a to b and this one from a to b as well. Okay, so if I want to do that, so let me continue now. So this becomes equal to minus 1/2. If u is ln of t, then what happens for du? Du becomes dt over t. And this means that v is nothing except t. Okay, so then I will use this formula uv, which in this case becomes t ln of t minus integral from 2 epsilon to 1. And then what do I have? I have v du, but v du. Yes? Okay, but that's very simple. Here I should also go from 2 epsilon to 1. Okay, so this becomes minus 1/2. And then if I replace t with 1, ln of 1 is 0, so it vanishes. Then I replace t with 2 epsilon, but I have a negative sign, so be careful. So it becomes minus 2 epsilon ln of 2 epsilon. Okay, and then what happens here? This t and that t are cancelled, and the integral of dt is simply t. I have to run it from 2 epsilon to 1. So it becomes 1 minus 2 epsilon, but there is a minus sign here, so it becomes 2 epsilon minus 1. Yes? And then I multiply that minus a half in, so it becomes epsilon ln of 2 epsilon. And then I have minus epsilon plus 1 half. Okay? And now I have to take the limit of this when epsilon approaches to 0 from the right hand side. But you can simply use Hopital's rule to show that this limit as epsilon approaches to 0 from the right hand side is indeed 0. And this one is also 0, so you get 1 half. Okay? So what does it mean? It means this integral is convergent and it converges to 1 half. And we learned that this function is less than this function. Okay? So this means that this integral from epsilon to 1 half as epsilon goes to 0 from the right hand side also converges. And there is a theorem, if the absolute value, if the integral of the absolute value of a function converges, the integral of the function itself also converges. Okay, so I was able to show that yes, J1 is indeed a convergent integral. Okay, but what I can do for the second part? Let me call it J2. Okay, so if I want to talk about J2, I have to write J2 to be the limit. For example, integral from 1 over 2 to r ln of 2x divided by 1 plus x squared dx. That's the way we actually do it, yes, and r goes to infinity. Okay, but instead of considering this integral J2, I know that ln of 2x divided by 1 plus x squared is less than equal to the integral of the function ln of 2x over x squared. Yes, because the denominator on the left hand side is 1 plus x squared, which is bigger than the x squared. So that's correct. And my claim is that the integral from 1 over 2 to infinity ln of 2x over x squared dx is indeed convergent. Okay? Again, I can use inequalities to prove that this integral is convergent, but this is one of those cases that you indeed can calculate the value of this integral. Okay? To have an extra bonus for this video, I would consider let us calculate the value of this integral as well. Okay, the first thing we do is to write this as the limit of 1 over 2 to r ln of 2x over x squared dx, and then r goes to infinity, and I will try to calculate this for you. Okay, so let me go to the next page. There is not enough space here. Okay, so let me call this integral k integral from 1 over 2 r. I want to write it intentionally in this way, ln of 2x here, and I would write it as 1 over x squared dx here. Okay, the reason I did it because I want to use integration by parts again. Okay, so I will give this the role of u, and I will give the role of dv to this expression. So now I need to calculate du. So du is very simple, so it becomes 1 over 2x in the denominator. The derivative of 2x is 2 in the numerator, and then I have dx, which becomes simply 1 over x dx. And then dv is 1 over x squared dx. Of course, this is very simple, that v is nothing except minus 1 over x. And now I use the formula for integration by parts, so let me write it again in front of you. So integral from a to b, u dv is equal to uv from a to b minus integral from a to b v du. Okay, so this becomes k is equal to u times v. This is my u and this is my v. I multiply them, so it becomes minus ln of 2x over x. But then I run it from 1 half to r. Minus integral from 1 half to r v times du. This is your v, and this is your du. There is a minus sign. I pull it out and make it positive here, so it becomes positive, and it becomes 1 over x squared dx. Okay, so now here I replace x with r, so it becomes minus ln of 2r over r, and then minus minus becomes plus, but I have to replace x with 1/2. If I replace x with 1/2, ln of 1 is 0, so it vanishes. So that's the only thing that I get. And then of course the primitive function for 1 over x squared is minus 1 over x. Then I have to run it from 1 over 2 to r. Okay, so it becomes minus ln of 2r over r, and then minus 1 over r plus 2. Yes? Okay, now I have to calculate the limit of this function as r approaches to infinity. Okay, so this limit becomes 0, this limit becomes 0, and then of course it is 2. So this means that the limit of k when r goes to infinity is actually 2. Yes, so this means that the integral from 1 over 2 to infinity ln of 2x over x squared is convergent, and it converges to 2. Okay, so this means we are done. Yes, so if I want to go back here, so I was able to show that this integral converges by comparing the integrand with this function. I realized that the absolute value of the integrand of this integral is always less than or equal to this one, and I realized that yes, the integral of this function within the range from epsilon to 1/2 indeed converges, so this guarantees that J1 converges. And then I started comparing this integrand with this function. We know that this is always less than or equal to this, and I was able to show you that this integral actually converges. And as a bonus problem, we realize that yes, the value of this integral is indeed 2. Okay, so now this guarantees that yes, what we did before, based on the assumption that this integral converges, is indeed a correct assumption. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.